Hey there again, math peeps. This is Mrs. Marshall with our last day of notes from Unit 5, and this is actually proofs. We are going to be proving trig identities. All of the identities that I gave you on the last notes, we're going to have to know those and use those to prove different equations that I give you for these notes. So let's fill in the notes. We will prove using the identities that various expressions are identities by simplifying. So just as we had to simplify last time, we're going to simplify again, but we're simplifying one side until both sides are the same. And that's essentially what we're going to be doing. There are some helpful tips on where I would suggest you start. So let's start on the complicated side. Complicated is this just the side that looks like it has more quote unquote happening. It doesn't look simplified. It's more expressions or terms than one side than the other side. Then you are going to simplify by distribute or multiply. So depends on what's happening, and that doesn't necessarily have to happen next after you start with the complicated side. Sometimes you don't have to distribute. Sometimes you might have to just make sines and cosines from the beginning, which is another suggestion. Or you should get a common denominator. Denominator. Ooh, that came out kind of crazy. And then you might also have to multiply by the conjugate. And we will review what the conjugate is. But these are some helpful tips. I usually start with number 1 and then look and see if I can distribute. Look to see if I can make sines and cosines. Like I literally do it in this order, but sometimes there is a row that I don't necessarily have to do and I skip it and do the next one. So let's solve. Number 1. Oh, before we solve, the goal. The goal is to always get an identity. So you want to manipulate the side so that you can get an identity. And once you're able to get an identity, then you can rewrite that as the identity, and maybe that'll simplify so that you can keep on simplifying until it turns into the other side, which is what you want it to be. So let's go ahead and do these 5 examples. Number 1. So the most complicated side to me looks like this left side. And we got to think about it. Okay, cosecant. First step, can we distribute? Nope, no distributing can happen. Sines and cosines can happen though. So cosecant reciprocal identity is 1 over sine theta times cosine theta. And again, this is the reciprocal identity. And I'm going to just abbreviate it. You don't have to put this every single time. I'm just showing you for the purposes of the notes. And then, now we can multiply cosine theta, sine theta. And cosine theta, sine theta, based on an identity, is cotangent theta. Because that is, let's change it to orange. That is the quotient identity. And we get what we want. We want the left side equal to the right side. So cotangent theta indeed equals cotangent theta. And we must end all proofs with these 3 letters, QED. And QED stands for something like, and thus it has been proven. So that's what we put QED to represent that the problem is over. We're done. Yes, it is not correct or finished if you do not put QED. So you must put QED. Number 2. The right side looks more complicated. So we're like, what should we do? Let's multiply. Let's multiply this thing out. Secant theta times secant theta is secant theta squared, or secant squared theta. And then secant theta times 1. And you can do a box, but for the purposes of these notes, I don't have that much space, so I'm not going to do a box this time. I'm going to do the regular old FOIL method. And -1 times 1 is -1. All right, what ends up happening right here is these two cancel out. So secant squared theta minus 1 is what we end up with. And we're trying to get it to be tangent squared theta. Oh, well, if I use my identities from last class or last notes again, this is a Pythagorean identity. And the Pythagorean identity for that is tangent squared theta. And so therefore we have proven the right side equals the left side. QED. All right, those two are a little simple. Let's get a little bit complicated. The number 3. All right, it's like which side looks more complicated? There is no one single term. So which side? Any, meeny, miny, mo. Sometimes you start on a hard side that you think you should start on, and then you realize, oh man, I should go to the other side. So you should definitely use pencil for these. So I'm going to write that down. Use pencil, because you will need to erase. All right. The complicated side. I think it's the left side. I could be wrong, but again, I have done these ahead of time because I want to make sure I'm doing them right. But the complicated side, you could start on the right. You might could get to the left, but I'm going to start on the left so I can get to the right. So, let's think. Multiply, distribute, sines and cosines, denominator, conjugate. Conjugate, I need to multiply by the conjugate. So sine of 3, or sine to the third power, or sine x cubed, all over 1 plus cosine x. When we multiply by the conjugate, that's just changing the sign in the middle to minus if it's plus, or to plus if it's already minus. And whatever you do to the bottom, you do to the top. We now need to actually distribute and multiply. For the top, remember, you're trying to get it so that you have sine x on the outside and 1 minus cosine in parentheses, so it's not distributed. So this sort of looks the same. I'm going to leave that undistributed and just write it like this. And then we multiply 1 minus, or 1 times 1 is 1. 1, and that's negative cosine x. And then cosine x, so it's positive, and negative cosine squared x. Well, when let me write that a little bit better. When we simplify the bottom, just like the previous example, the cosine x and negative cosine x cancel. So you end up with sine cubed x, 1 minus cosine x. And if you know that the answer is 1 minus cosine squared x without multiplying and foiling it all out and writing all the terms, that's perfectly fine as well. So now we got to try to think, what can we do now? Remember, again, the goal is to get an identity. Do we see an identity situation happening? Yes. This right here is a Pythagorean identity. And so this is sine to the third x times 1 minus cosine x all over, and that identity is sine squared x. Yes. So now, got to keep thinking about what we're trying to get it to be. One single sine x with that 1 minus cosine x beside it. What can we do? Well, this sine squared x will go away, and this sine cubed x will also go away, but this will end up being a 1. We don't write 1s in our answers, so this ends up being sine x times 1 minus cosine x, because the bottom, it all completely goes away. Yes. So we have solved, and the left side equals the right side. And thus it has been proven. Yes. All right, next one. And as you can see, out of the three I've done, you don't do all of them the same way. You literally just have to use the tools that work best for that situation. All right. Any, mini, miny, mo. What side y'all think is the most complicated? Hopefully you said the left side. All right. Now we got to figure out what in the world we're going to do. So I look at those suggestions. Okay, complicated side, got it. Distribute, no, I can't do that. Sines and cosines, yeah, I can do that. If I multiply by the conjugate like I did before, I'm just going to have a bunch of tangents and cotangents, and I'm trying to get one simple little cosine. So yeah, let's change this to sines and cosines. So this is 1 over sine theta all over. Okay, how do we want to change tangent? Do we want to change it to its reciprocal 1 over cotangent? Oh, no, we want sines and cosines. So sine over cosine plus cotangent is cosine over sine. All right, next thing, let's see. Oh, we can get common denominators. So our common denominator would mean this one needs a sine and this one needs a cosine. And once we solve that, or once we multiply that to both sides, to solve it would mean all of this is my new numerator because my denominators are the same. And so this ends up being 1 over sine theta all over sine squared theta, because I just multiplied, plus cosine squared theta, because I just multiplied, all over sine theta cosine theta. All right, and I'm going to make this in the middle fraction line a little darker, and that's representing this line up here. Okay, let's see, what can we do now? Any, mini, miny, mo. Oh, I see an identity. This right here is the Pythagorean identity. And that just means that on top is 1. So this is 1 over sine theta all over 1 over sine theta cosine theta. All right. Let's see, what can we do now? We might have to keep change flip. So when I solve these to save on space, I know I'm going to multiply this up, and therefore that's going to change to multiply, and that means I'm going to flip sine theta cosine theta, and the whole denominator is now gone because I'm changing the times, and I'm flipping. Okay, so now let's see, what in the world can we do now? Oh, we can cross simplify. And I'm going to slide this over just a tad. There we go. So if I cross simplify just the top, sine theta and sine theta goes away. Or without cross simplifying, you can multiply straight across and you end up getting, so I'm going to just multiply straight across, sine theta cosine theta all over sine theta. And now you can cross simplify. Hopefully you can see it better in case you didn't see it before. Sine theta and sine theta, they simplify. And this is cosine theta over 1, which equals cosine theta. And therefore, we have done it. The left side equals the right side. Q, E, D. If I had more room, I would keep going down vertically, but I ran out of room, so got to end the last little part horizontally. Last example. Let's see what we can do. Oh, we definitely can tell which side is the most complicated. All right, let's see. Distribute or multiply, can't do that. Sines and cosines, yeah, but I got that 1 out there. Denominators, oh, I might need to get a common denominator. So let's make that 1. So then our common denominator would be multiplying 1 plus sine theta. Not cis, sine, honey. Okay, times 1 plus sine theta again. And so we end up with 1 plus sine theta minus cosine squared theta all over. And remember, it's essentially this part because your denominator stays the same. This and this are the exact same. 1 plus sine theta. All right, let's see what else we can do. Okay, we don't want to multiply by a conjugate. Not yet. That'll make it real messy on the top because that'll be foiling. Do we have an identity? Yes, we do. This cosine squared theta is a Pythagorean identity. And we can change that. Oh, wait. Let's move it around so that the 1 and that cosine squared theta together is the Pythagorean identity. So it'll be 1 minus cosine squared theta plus sine theta. I just literally rearranged it. And so now we have a true Pythagorean identity, this part right here. And we can rewrite it, but don't forget about your denominator, 1 plus sine theta. All right, so now rewriting that is sine squared theta plus sine theta all over 1 plus sine theta. We're getting close. We're getting ready to get a single sine theta. Let's see what else we can do, though. Sine squared theta plus sine theta. Oh, I know. Let's pull out a sine theta. Sine theta and sine theta plus 1. So let's factor. Again, we are going to factor. And we leave this with 1 plus sine theta on the bottom. Oh, snap, crackle, and pop. 1 plus sine theta and sine theta plus 1. They cancel out. And our final answer is sine theta. And sine theta equals sine theta. And thus it has been proven. All right, you will have plenty of these to practice in class. This is the ultimate goal of this unit, is to be able to prove using trig identities. You got this. You got it. Until next time, Marshall out.